Hey, everybody. Thank you so much for coming out today. Good. Hey, everybody. Thanks for coming out today. My name is Brian Warner. I'm going to be talking about a file transfer project I've been working on called Magic-Wormhole. If you go to magic-wormhole.io, that'll take you to the GitHub page. There's a copy of the slides if you want to follow along. You can take a look at all the code. The obligatory biography. I've been working in Python for about 15 years or so. I created BuildBot a long, long time ago, in case you've heard of that one. The most recent thing I've put together that is getting some more usage is called Versioneer, so a little package to update your version every time you do a git commit. At a startup called All My Data, I helped build a system called Tahoe LAFS, a distributed encrypted storage system that's getting a little bit of traction. At Mozilla, I worked on Persona, I worked on the add-on SDK, I worked on the original version of Firefox Sync, and fans of the JPEG process there will probably recognize a few things in this project. And these days I'm working on Magic-Wormhole. You can follow me on Twitter, Lothar with the triple R, or GitHub, Warner. So Magic-Wormhole is a file transfer program. This is about moving a file or a directory or some little bit of string from one machine to another. I bet everybody in this room has done this at least a dozen times in the last 24 hours. It's something that we do all the time. You might have used SSH to copy it from one place to another. You might have attached it as in an email message. You might have put it into a shared directory where your coworkers could get to it. The use case for this is any of those. If you've got a cat video on your computer and you really want to give it to the person next to you, it should be easy to get it there in a safe, secure, simple fashion. I'm hoping to convince you that this tool is both easier and safer than all of the other tools, all the other techniques that are typically used for this kind of thing, especially when there's not already a relationship between those two machines. So, you two are sitting next to each other, the humans know each other, but the computers don't yet know about each other. That's a use case that is usually solved with tools that I think are harder and less secure than this one. So what does it look like? First off, you do pip install magic-wormhole. Please do that into a virtual env. We saw Glyph's talk yesterday about why doing this into your root is a bad idea. Then on the sender side, there's a command line tool, and you run wormhole send, and you give it the file name. That gives you a wormhole code, the string that prints out, the 7 guitarist revenge. You transcribe that. You get that to your recipient. So as one human to another, you give them this string. The other person runs wormhole receive. They type in that string. Given that, the two programs can find each other. They can negotiate a shared strong session key. They can encrypt the file, figure out how to get bytes from one side to the other, transfer it over, check the hash, acknowledge it. The kind of fanciful way I like to think about this is two wizards who are standing on hilltops on far sides of the planet, and they speak the same magic spell into the air at the same time. And someone goes, 7 guitarist revenge, and that causes this wormhole, this portal, to pop open between them. And then they can kind of throw files and stuff through it. Things pop out on the other side. So think of that, and you'll understand Magic-Wormhole. So the wormhole code is kind of the key to this. It's a string that goes from the sending computer up to the sending human. The sending human reads that off the screen. The sending human transcribes that over to the receiving human via some channel. They could speak it, they can IM it, they can send it by email, whatever. And then the receiving human types that into the computer. So this is, at its heart, a way of getting two computers to meet each other via these two humans that have already met each other. So the human's job in this is to get that code from one machine off to the other. Now, you might think that file transfer is a solved problem. I mean, FTP, everybody here has probably used FTP at one point or another, or you're too young to have been born when the FTP RFC was actually published in 1980. This has been around for so long. What's wrong with that? What's wrong with the tools that we're currently using for this? So you can characterize these different tools by the amount of data that one human has to transcribe to the other. That's kind of the limiting factor in a UX thing. And I argue that all the common tools we have actually take more work and are less secure than this approach. So if the most obvious thing I might reach for is to include this file as an email attachment to you. In order for me to send you a file that way, I have to start by getting you to tell me your email address. So this email address has to travel in the opposite direction, and you have a transcription problem. I have to hear what you're saying and figure out how to type it accurately. And in the best case, you have an email address that's easy to spell and easy to understand, and it's at some popular short-named provider. But in the worst case, most email addresses tend to be big and long and random because you're fighting for this contentious namespace at one of these providers. Another approach is to upload it to a server. If I have a server ready to go, and I can think of a unique path on that server, and I upload it, then I can dictate to you an even longer string. I have to tell you the domain name of my server and the path that I've allocated on that. You can upload it to something like Dropbox, which is a nice, easy way of getting a file into a particular URL. But the URLs there are even longer because they have an even more difficult contention problem. You have a longer, more random string that's not human selected. And the problem with all of those cases is that there's all these intermediaries that get to have access to the file that really don't need any access to the file. So the server that you put it on, the network links in between you and your recipient, if it's protected by TLS, great, but you're still vulnerable to the certificate authorities in the PKI world. You could transfer this over on a USB drive if you happen to be sitting right next to each other, but USB drives are kind of hard to erase. Flash memory, doesn't forget quite as well as you would like it to. So now, in terms of the security aspect, you have to think about what you're going to do with that USB drive next. And in addition, it's a little bit sketchy to take other people's USB drives and put them into your computer. There are enough bugs in the kernel drivers these days. You don't know what's going to happen to your system when you do that. Using SSH takes care of the security problems, but transforms the UX problem into getting your public key onto that other person's machine. If you've got a cat video and you wanted to give it to him, they have to give you an entire account on their machine, and then you have to get that entire public key over to their machine. And that's far too long to actually dictate. So nobody does that, and you end up using some funky password thing for that bootstrapping part. In contrast to all of those, in magic-wormhole, you send a very short string that's carefully designed to be transcribable and dictatable from the sender to the recipient. And that one string is the entire security, the entire accessibility path. Anybody in the world, any wizard on that hilltop that says that same magic-wormhole code at the same time gets that one file, and nobody else. So if I've convinced you now that this is the easiest and safest way to move a file from one machine to another, then you probably want to know how it works. There are a couple of different phases to the protocol. It starts with a message exchange, so the two nodes can just find each other and start exchanging messages at all. Then there's a key agreement phase where they use an algorithm called PAKE that I'll be telling you about in a little bit that lets them agree on a session key. Then they try and exchange their IP addresses. They try and use different techniques to get a direct connection between the two of them. Once they have that connection, they can run an encrypted data transfer protocol over that, move the file over, get the acknowledgement back. So the clients exchange their initial messages through a rendezvous server. This is a simple relay that accepts messages from one side, hands them out to somebody who asked for them on the other side. This is something that I run for this particular program. The rendezvous server doesn't participate in this conversation, it's just facilitating it. And it's necessary because when this starts, the two clients don't know anything about each other than there's somebody else out there using the same wormhole code. So the first part of that wormhole code is the channel ID. In this example, channel number 1, but the numbers are just short integers. The server allocates those. The channel ID tells the server which two clients coming together using the same channel ID get messages from each other. The wormhole codes in general can be short because they cheat. The URL for this service is baked into the client. Any two applications that are using the same wormhole mechanism will use the same server. And so you don't have to include it in the wormhole code. So in a lot of those other examples, like uploading it to an FTP server, uploading it to a Dropbox thing, you have to include a domain name there to provide that context. The clients make a WebSocket connection to this machine, and they exchange 3 or 4, maybe 5 messages by the time that they're done. Now, here's the really fun crypto part. So the first message they send across this connection that's being facilitated by the relay server is using a protocol called PAKE. PAKE stands for Password Authenticated Key Exchange. It is actually a family of protocols. There are a bunch of different ones that have been developed. First one came out in the early 90s. SRP is probably the best known one, but the security proof on that is not really very good. It was kind of before we knew how to design protocols well. There's one called JPake that we used in the first version of Firefox Sync. But these days, the one that is preferred by the community is called SPAKE2, which was made in 2005. These protocols allow two parties to turn a weak shared secret into a strong shared session key. So it's basically a box on one side, and you put something like a password into it, and it gets to exchange messages with its peer on the other side, and then at the end of the day, what pops out is a session key. And The rule is that if both sides put the same password in, then both sides get the same key out. And if the passwords are different, then they get keys out that are random and completely unrelated to each other. So this is a protocol that lets you take any short string and expand it into something larger that you can use for subsequent messages. So SPAKE2, I'm not going to go into a great amount of detail on the math here. Feel free to talk to me later if you want some more details. But if you're familiar with Diffie-Hellman key exchange, key agreement, two parties agree upon a shared key, where you have one side sending G to the X and the other side, or G to the A, and the other side sends G to the B, and then you compute G to the A to the B and G to the B to the A, and because of commutative, those two things are the same. It's like that, except that the message that you send gets blinded by a factor derived from the password before you send it. So that U to the PW is the blinding factor that Alice puts on, and then Bob divides by U to the PW to take that blinding factor off before he uses it. So if the two sides are using the same blinding factors, then this behaves just like regular Diffie-Hellman, but you know that you could only come to the same key if the other person had exactly the same blinding factor. And because of the way that exponents work inside this kind of modular field, this is a random mapping, and there's no way of knowing what that G to the A was unless you happen to have that same blinding factor. So this is super cool. I really love this algorithm. I wrote a pure Python implementation of this. It's using the ed25519 curve so that it's pretty fast, even though it's in pure Python. It has nice short keys and is super secure. And this one takes about 14 milliseconds to run. If we used the C implementation of this, you could probably improve that by a factor of 10, maybe 100. But it's good enough for an application like this, where most of the time you're blocked waiting on the user to type in the thing. So PAKE is pretty awesome. It means that with a weak secret and some interaction, you can get to a strong secret. And it's basically trading off, it's spending interaction in order to prevent offline attacks. A passive eavesdropper who's watching your messages go by gets zero information about what your session key is. An active man in the middle, the best they can do is try to pretend to be Alice, try to pretend to be your conversation partner, and try to guess what that key is. And if they succeed, then they can get in the middle, they can see your messages. But if they fail, you know that they failed. And they only get one guess. So this is great because even a short string, you can afford to allow somebody a 1 in a million chance of guessing something if they only get one guess at it. And that's not true for offline things like encryption keys or passwords. The wormhole codes are the input to PAKE. So the wormhole code is generated by taking the channel ID that you allocated from the server. There's a word list. I'm using the PGP word list that I think was used for PGP phone or Z phone. And it's a list of words designed to be phonetically distinct, so you can recognize them when they're coming over an audio channel. There are 256 words in there, os.urandom, choose one. So the default configuration is using 2 words, and then this whole thing is fed into PAKE. That configuration gives us a 16-bit secret. You can change that. There's an option to use more words if you feel like it. But that means that there are 65,000 codes. These are single use, so each time you send a file, you get a new code. Every time, if you want to send a new file, you get a new code. You establish that new connection. And it has this really nice property here where the user, each time an attacker tries to guess this and fails, the user sees the failure screen. So they see a message like this, where I've tried to send your file, something didn't go right, either you or your correspondent mistyped the code, or somebody tried to attack you and they lost. They guessed and they guessed wrong. You can try again. That's going to give both you and the attacker a second chance at this. So because the size of the key space is large enough to keep the attacker from getting a good chance of getting through, the user has to be really, really, really patient and run this over and over and over again to give the attacker a better chance of going through. So you'd have to rerun this protocol and retranscribe this string to your friend 650 times before the attacker has even a 1% chance of breaking through. And it's this nice and relatively rare situation where the laziness of the user improves the security. Their unwillingness to continue in the face of constant errors is a good thing. It's like I had to reload the footgun multiple times. OK, so that's enough about PAKE. Once the session key is established, and they both have the same shared session key, then they can encrypt all of their subsequent messages. So everything else in this protocol gets encrypted from a key derived from that first one that comes out of PAKE. And this is kind of where the network plumbing aspect of the project takes over. So after that phase is done, then the two sides use ifconfig to find out all their local IP addresses. And they listen on a TCP port. And then they send a message encrypted with a session key to say, hey, I'm listening here and here and here. And Bob says, I'm listening here and here and here. And they try to connect to all of those. And the first connection that goes through and successfully answers an encrypted handshake, also derived from that PAKE key, is the winner, and it stops using all of the other one. This works out OK as long as one of the two sides has a public IP address, so like one is a server that you're connecting to, or both sides are sitting on the same local network. So two people sitting next to her that want to exchange the cat videos, they're both on the PyCon network, their local addresses, their 10. Or 192.168, will be able to see each other. And if you're moving something server, they can see that one. But if you have two people, say you are calling my dad on the phone to say, I want to send you this file, the code is blah, blah, blah. He and I are both at home, both behind our NAT boxes. Those machines can't get to each other directly. So in this case, the client falls back to a relay server that I also run here. If you're familiar with stun and turn, this is the moral equivalent of a turn server. It's, again, just a data relay. It accepts two TCP connections that want to talk to each other, and it glues them together. It's called the transit relay. This is not ideal. I'm working on adding techniques to do NAT hole punching to increase the frequency of connections, the probability that a connection will be able to make a direct connection instead of going through this relay. But for the kind of traffic volume I'm expecting here, I don't expect this will be a big problem. And I just run this on a VPS somewhere off in the cloud. Once that handshake is complete, then the actual file data gets sent through an encrypted record pipe. So this is using the NaCl secret box. This is using libsodium, the Python bindings to that. Each record gets encrypted by a unique nonce, gets sent. There are different keys in each direction. All these keys are derived from that same original PAKE master key. And as the data gets sent over, it gets hashed. The receiving end is hashing all of those bytes, and then the acknowledgement message says, here's the hash of everything that I've received from you. So that's a good, strong way to making sure a record didn't get dropped or some funky network error caused something to get dropped. The secret box function is an authenticated encryption cipher, so flipping bits, an attacker trying to flip the bits along the way, that gets detected as soon as a single record goes by. So that's how the application works. This is built on top of an API that you can use in your own applications. Each application that wants to use this has an application identifier that scopes the channel IDs so that two different applications using different identifiers aren't fighting for each other for the short, easy-to-transcribe codes. There's a relay URL that you pass into the application, and the one that I run that people are free to use is in a file. It's just a constant definition inside the package. You then set the code. You can also ask the wormhole to allocate for you a brand new code, and that'll go to the server and find a channel. You can actually have, let's see, there's another call called input code that does tab completion on the words as you type them in. So when I'm typing in 7 Guitarist Revenge, I only actually have to hit tab, and it goes to the server and says, there's only one channel allocated right now, and that's 7, so let me fill that in for you. And then I type GU, and I hit tab, and there's a couple of words that start with GU in the list, and it shows me what they are. And so it's actually really fast to go and type these things in. And if you think about it from an information theory point of view, you're only entering in 16 bits of data. So obviously, you should be able to do that with a very small number of keystrokes. But it makes it something nice and easy to transcribe and easy to pronounce. Then you send byte strings, and you get byte strings back. This works in both Python 2, Python 3.3, 3.4, 3.5, maybe PyPy, I'm not sure. The API handles all the network protocols, all the encryption, all that is taken care of under the covers. And by the end of the sprints, I will have both the blocking interface to this and the twisted interface to this. I broke the blocking interface about a week ago when I was making some major changes. So the directions that I want to take this, I definitely want to have a nice, easy GUI application for this. This is calling out for something better than a command line tool. And you should be able to drag and drop a file onto it. It shows you the code. You should be able to click a button and type in the code, and a file pops out into your downloads folder. I think it'd be great to have a browser extension for this, probably even a deployed web page form of this. The protocol is speaking WebSockets to the relay rendezvous server specifically so that I can then have a web-based form of this interoperate with a command line base. I'm looking to add to the range of transports that it can do. 2 browser-based implementations could totally use WebRTC to connect to each other and avoid having to use my relay server. Other people smarter than me have already figured out all of the stun, turn, stunned, ice kinds of stuff, so we should be able to take advantage of that. Running this over a Tor onion service is a great way of bypassing the NATs, the NAT barriers. I'm hoping to try and get the SPAKE2 algorithm added to libsodium, and that'll make it easier to extend this to other languages, so that there are lots there are Go bindings and Rust bindings and JavaScript bindings to libsodium, and this would make it easier to write a client for this in those other languages. And then I'm really interested in seeing this used beyond file transfer. I want people to think of this as a tool that they can use in their applications anytime you need to deliver a credential from one place to another. So think about you have your mobile app, and to attach that mobile app to an account on some server, it needs to have some token. Or you have 2 client devices, and they want to go and talk to each other, some kind of messaging thing. And you need a way of getting a key from one of those machines to the other so they know about each other. A lot of this comes down to that same introduction task, where there are 2 humans that know about each other, and they have their devices. And the humans are introducing the devices to each other. It's like, hi there, Bob, this is my computer. And it's more like, hi there, Bob's computer, this is my computer. And you want to connect those. So provisioning a client in this sort of world would, the old way, the typical way this is done, is to go to a website, create an account, type in a password to that account, remember the password, deal with the fact that people generate really lousy passwords. It's just outstanding how bad passwords are from a usability point of view. And then you install the mobile app, and you type the same password into that. So passwords are bad. Remembering passwords is a hassle. Another approach, if you have a tool like this, is that you go to the server and you say, I'd like to add a new device. Tell me an invitation code for it. Tell me a wormhole code for it. And then you type that into your phone. That runs this protocol, and it gets a token dedicated to that one device. And now you're done. You could set it up so that you ask the server to email you a code. A nice thing about these codes that I forgot to mention before is that they're forward secure. Once you finish that PAKE message, once you exchange those 2 messages, you can reveal the code and not lose any security. So it's a single use, and it's not secret outside that really narrow window from the time you start that process to the time that the other side sends their message. So the fact that this code is still sitting around in email for a long period of time doesn't hurt you. Same reason that you'd never email password resets. You never send the new password out in email. You send a token that can get used a single time to go and reset it. In a messaging app, something like Signal, so the crypto in Signal is great, but the way that it works is that when I want to talk to Bob, I ask the central Signal server for Bob's public key, and then I start using that. There are some hidden options in there to let you verify the key. If you meet Bob in person, you can compare your keys. But fundamentally, you're depending upon that server to give you the right key. And the model that I like to see is where I'm standing next to somebody right now, and I want to get our 2 machines to know about each other. So I should be able to go to my device and go to the address book and say, plus, invite somebody, and it says, here's the code. And they type in that code, or, I don't know, QR code, something. The 2 devices have that physical proximity right now. They can leverage that to transfer something small across, and then use this protocol to ask each other for the full-blown public key, so that you're not vulnerable to anybody outside of this ecosystem other than those 2 programs. So the real reason that I'm building this tool is because PAKE is a really interesting cryptographic tool that is a primitive that we should be able to use, and it's not yet in our toolbox. The history of cryptography and of techniques has this really long lag time. Symmetric encryption is something that I'd say, maybe half the developers that I talk to are comfortable using that in a product. Some of them think it's a little bit, out there. But it's been around since, Julius Caesar days, right? Like 800 BC, what? So there's a set of tools that are slowly coming into general use. Signature hashes, most people are comfortable with hashes at this point. Digital signatures, that's showing up in a lot of applications. Public key cryptography, it's been around for 50 years, and it's still just becoming something that people are comfortable using. PAKE has been around since the 90s. It enables a lot of really interesting use cases and really a lot of interesting operational modes. But I think to get it into the hands of developers, you need to have some clear examples, some clear, the academic community needs to say, this algorithm is good. Use this, and it'll do what you expect it to do. You need libraries that are easy to use. You need applications that use it so you can feel comfortable. You can say, I'm not going this alone. That person over there is doing it. Everybody's doing it. Maybe it's OK for me to do it too. So file transfer, it's a kind of pedestrian application. I found it to be really handy myself, actually, more convenient than SSH, in some cases, just moving files between my own servers. But it's not exactly an exciting use case. But it is kind of a foot in the door. You know, being able to use PAKE, being able to use a short secret to bootstrap to a larger secret is the rest of the stuff that I want people to have access to. So of the stuff in your toolbox, let's add PAKE to that list. So that's a project. If you go to magic-wormhole.io, that'll bounce you over to the GitHub page where you can take a look at a copy of these slides, the code. Pip install magic wormhole is how you get it. That gets you the wormhole binary. And you can send me email or contact me on Twitter, Lothar with a triple R. Thank you very much. Oh, and I have stickers. I'll take questions, and I'll throw out stickers. And if you want questions, please come to the microphones in the 2 aisles there.
All right. I have a question. So for that initial relay, right?
The initial relay, yeah?
Yeah. I have an app ID, which I imagine is not private information. It's kind of public. It's stored. It's shared with your clients and whatnot.
Yeah.
Then I have a channel ID, which is meant to be private, and then the 2 words, right?
Yeah.
What stops a malicious third party from just spamming your relay server with the same app ID and random channel IDs and all that?
Nothing. This one problem with this approach, with this protocol, is that it's kind of vulnerable to denial of service attacks. Because there's so little information somebody needs to participate in it, there's not a very high barrier to prevent somebody from participating in it. So my thoughts for that are to add a layer on top where you have to get, there's some sort of rate limiting thing, right? It's like, I have to go to some central server to get a ticket that allows me to submit a message to that rendezvous server. And the person who's trying to do the denial of a service attack runs up against some rate limiting boundary. Maybe you do a CAPTCHA thing, maybe you have to be signed into some other service, and they can count how many tickets people are requesting and then terminate that as an abuse thing. So it'll be something in that category, I think. Yeah?
Is it correct that the PAKE process to derive the session key requires real-time communication between the sender and receiver?
Yes. It doesn't, not strictly real-time, but it requires a couple of messages to be exchanged. So PAKE emits one message and then waits for one message coming from the other side before you have the shared session key. Then there's a key confirmation message to make sure that somebody really did get the right session key and not something else. And then you send all of your regular messages. I'm working on a mode of this that's more persistent. So at the moment, it makes that WebSocket connection. If that drops, then the server abandons the channel and you have to start again. So these 2 programs have to be running concurrently for at least a couple of seconds in order to make this work. The persistent mode that I'm working on would be more store and forward and come back again later, so that in a longer running, like a messaging application, it could be start the process, shut down, turn on again tomorrow, get the receipt, send the next message, do it again there. Yeah.
So my question comes from the tab complete.
Yeah.
So say there's only one channel, 7,
Sure. Yep.
and you put in the G, you can now tab complete and see the things. Doesn't that make it easier to guess? Or because maybe there's only 5 keywords that are currently in use?
but you're not revealing to the attacker what you hit before you hit tab.
Gotcha.
So it's your local agent that knows the fixed list of words that the codes were chosen from. And then it's just an easier affordance to get to that word faster. The total amount of information you're typing in is still 16 bits. And you can almost think of it like G tab is like Huffman encoding when you have a fixed alphabet. One thing I'm looking to add to it is a way to have alternate word lists. So when you get the channel, when the client goes to the server and says, hey, I want to use channel 7, it can say, oh, I got this hint from the other side that we are using Dutch for this particular word list. So switch to that alternate word list. And then you're not losing any more information than you would if you didn't reveal that, because you were only using 256 words in any given list anyway.
Gotcha. This is a cool package.
Thank you.
So 16 bits of entropy.
Sure.
And it's time-bound.
Yeah. And single-use bound.
Single-use bound for one file, that's cool. However, you're providing a library. Developers are going to use this for all sorts of things that you didn't expect.
Yeah.
I'm imagining someone building like a backup software. So I transfer the contents of my whole hard drive to the server.
Yep.
Now we're talking 500,000 files. That seems like a much bigger attack surface than you are anticipating in your example use case.
Yeah.
Have you thought about that? How do you want to mitigate it?
Yeah, the way to characterize the attack rate is going to be an attacker chooses to attack some percentage, some fraction of all the connections that are going through there. They're going to be successful with some other fraction of those attempts, depending on how long that word length is. And then they'll be successful with whatever, you know, if somebody attacks every single connection once, the worst case attack here is probably where somebody is camped out on your server, they watch all the connections going through, and for every single attack they do, they attack once, and if they fail, then they don't touch that ever again. So any individual user is protected by that laziness thing, because nobody's ever going to rerun this program enough times to be seriously vulnerable to it. But if they only ever attack any given person once, then maybe people will just be convinced that this program is kind of buggy and you have to do it a couple of times to make it work. And then the attacker will successfully manage to get, you know, 1 out of every 65,000 of those people. The mitigations for that would be, first, you're using this to establish a relationship. Looking to add a mode where once you've connected to, once you've transferred a file over there once, then it remembers a strong session key and uses that for next time. So that reduces the rate at which you're creating these things. You can also add extra words to this. You can say wormhole send -- words equals 4 and get a bigger code space. And there are some post-connection verification options. Wormhole send -- verify will show you a hash of the session key afterwards, and you can verify those yourself before you continue forwards.
Okay. So it sounds like you're not really protecting against developers that are using this to send many of these at one time against a determined adversary.
I am expecting that this is a kind of thing that is being run at human scale. Like there's a person driving this each time. Cool. If you have a machine driving it, then you can get a longer term, stronger key and keep on using that.
Of course.
So yeah, I think you're right.
Cool. Thank you.
Yeah. Hey, Pete.
I have a totally different kind of question, and that is, I was just wondering who supports, you know, your work on this? Is it the Navy?
This is me. This is me
you,
because I want to see this protocol and this technique made available in more places. So I'm totally willing to spend the $20 a month to run the VPS to
yeah, I mean, but your time is just.
Well, I am recommending that if people use this in a serious application, you may not want to depend upon me running this thing. Sure. And so the server that backs this is part of the same distribution.
But your development time is just you're just.
Yeah.
Yeah.
Yeah, this totally side project.
Yeah, I mean, like, as somebody who could potentially use this, like, this is the kind of basic research we as a community need to be supporting.
Yeah. Last question?
So the attacker scenario you're looking at is more like eavesdropping and getting information, but what about just an attacker trying to not execute denial of service?
Yeah. Like I was saying earlier, it's kind of vulnerable to that. Somebody can go through and just try to claim every single channel and just block other people's use of it. And so best I can think of is CAPTCHA of some sort to kind of slow that down.
Got it. Thank you.
Thanks. Thank you, everybody. Come on up. I got some cool stickers.